Hi, I'm Software Development Participant 604711.
And I'm participant 60712. Thank you for spending this time to review our project.
Last February, we witnessed a scary accident when a fellow student fell off his bike. It was so bad that his helmet broke, but he was able to get up, throw away the helmet, and keep going. We always wondered if he even mentioned it to his parents. I wouldn't. This entire incident made us curious, so we decided to find out how common bike accidents are. We did some research and realized that there are over 20 million unreported bike accidents every year, and these numbers are on the rise.
And this is how we came up with the idea of creating a program that can reproduce an accident. Our project is unique because it can test complex accidents compared with simple, direct impact, which is currently being used in the industry. With this software, you can take a recorded movement of any real-life accident and be able to replicate it. Eventually, we can build a database of hundreds of recorded accidents and consistently validate how devices like smartwatches or helmets perform for each and every one of these accidents. This clip shows our project's main objective. Above is the model accident that we analyzed, and below is a Fusion 360 simulation using the software we created. Follow the wrist of the dummy as we are tracking and extracting the position of the smartwatch. The position data will feed into the machine below. Now, observe the vertical carriage as it moves in sync with the dummy's wrist. Through this process, we are effectively replicating the motion of the wearable device during an accident. This will allow us to validate if the smartwatch's accident detection works as expected.
The first step for our project was to extract the data. We used a stage accident that we found on YouTube as a model. We had to crop the video to include only the accident, so we only kept about 1 second before and 1 second after the crash for data extraction. Now we were ready to use the tracker application to obtain positional, speed, and acceleration data of the dummy's wrist during the collision. Extracting the data was the easy part of the project, and this is when the tricky fun part started.
Upon extraction, we realized the data had a lot of errors due to noise and artifacts from real-world instrumentation. Therefore, it had to be filtered. We applied filtering logic to create a smoothed dataset from the raw data stream to eliminate noise and interference by using a moving average over 20 data points. As you can see in the graph on the left, the data is really choppy. If left like this, it would damage the motor of the testing machine due to the sudden changes. On the right, you have the smoothed data, which is the one the machine will use to duplicate the accident.
As mentioned before, the program utilizes the concept of moving average and runs it through all the position data. The data needed several filters in order to reach the point when it is duplicating the accident but not damaging the machine. The original exported data had 300 values which created the choppiness. So instead, we use every 10th value from dbo.wristData and place that in dbo.data for processing. Therefore, the program only needed to use 30 points. After 3 tables, 10 functions, 1 stored procedure, and 468 lines of code, we are now ready to test it with our machine. This procedure can now be duplicated, and we can replicate any type of accident, not just bikes. The social value of this project is that it can create reassurance to people that if they ever get an accident detection device, they will know that it has been thoroughly tested by being put to the trial with an accident that occurred in real life. This idea of simulating an accident could also lead to the creation of a universal testing standard that all accident detection devices would need to meet before reaching the market. In an educational light, children and engineers can use this device not just for bicycle accidents, but any complex movement. As a result, professors of physics can use the device to simulate various movements to demonstrate the different parts of kinematics or forces.
This procedure can now be replicated for any type of accident, not only bikes. This will allow companies who create devices with alert systems for accidents to calibrate their devices for a variety of scenarios. It will also increase people's trust in such devices and make them more likely to use the apparatuses. Just like 30 years ago, helmets were unusual, and today they're very common.
Thank you for listening.